Happy Wednesday, guys. It is Mr. Citro here. We are working our way through this third week, and this is really a review week. A little lighter on the assignments to help you stay caught up and to help you prep for this quiz on Friday and the unit exam when we return back to school, which will hopefully be soon. But as long as they can mediate everything going on, we can ensure it's going to be safe. So let's cover, yesterday you guys kept working on your classroom questions. Today we're going to have a meeting at 10:30 to 11. If you have questions, feel free to join. Any review stuff, please let me know. And finish up the geologic review for now. Tomorrow what I'm going to do is I'm going to give you a little bit of a practice assignment to help you review for the quiz, or we'll start the notes. I'm just going to see where we are at, base it on how well everyone's doing today. So let's take a look at the bell ringer. Here's the bell ringer, all about radioactive decay. So really quickly, just wanted to do a quick recap here. So radioactive decay, remember, this is on page 1 of your reference table. And these products here are stable. These are what we would call the daughter products. They're stable products. These portions here are radioactive. All right, so the products are stable, and your isotopes, remember these are called isotopes, are radioactive. And they want to break down, and half of them break down to a stable product every half-life, and each half-life has a specific time, and that is why radioactive isotopes are a good indicator of age. They decay at a predictable rate. Environmental factors do not change how fast they decay. So if I were to break this rock down into pieces and burn it, it would still have the same amount of carbon-14 and it would still decay at the same rate. Okay, so radioactive isotopes have an uneven or unbalanced protons to neutrons in that nucleus. They're not in their happy state, their stable state, and because of that, they're radioactive. They decay. That decay is predictable, and it produces 1/2 of a stable product every half-life. So let's take a quick look up here before we get going. So originally, 0 half-lives, 0 years old, 100% is radioactive in this case. Parent isotope, it's called. Now this is U-235. We use U-238. There is a difference in terms of how many years it takes, but the process is the same. After 1 half-life, okay, so 1 half-life means half of it decays. We have 50% of the parent that is an isotope and radioactive, and therefore we have 50% stable. Remember that the sum of these two always equals your original amount. 50% plus 50% must equal 100. Now this unstable isotope is radioactive. It can break down even further. So 50% of it is then broken down. The other 50% of it, okay, which technically is 25% of the original amount, 50% of this small portion here, ends up becoming stable. So we really see, again, this initial 50% here was from the first half-life, and then we added another 25% from the second half-life, making the total 75%. And half of 50% is 25%. And yet again, 25 plus 75% yields an original amount of 100, so we know that we are on the right par here. That would be the second half-life, and this process continues. Remember, it continues until we have so little of the parent isotope that we cannot accurately date it. Carbon-14 tends to be one that we see a lot for you folks, and that half-life ends around 60,000 years. Now, the half-life doesn't end, it continues, but the percent of carbon-14 that is radioactive is so little that we do not have technology or lab equipment to measure it accurately. So after about 60,000 years, we then need to change into a different isotope. We have only 4 isotopes here that we're going to talk about. There are hundreds of isotopes, and they all have different half-lives in terms of ages. So once one becomes too little, all right, once there is not enough of one type of isotope, we can just change to another. So here we are. 4 practice questions. If radioactive material X was heated, the length of the half-life would do what? So you're saying, oh, well, if we're going to heat it up, maybe it would get shorter. Remember that there is no change, okay? It remains the same. Environmental factors do not change half-life, ever, okay? How long would it take for one half-life of this unknown material? So we look up here and we start with 100% of the radioactive material. After one half-life, there is only 50% left. So we follow it down. This is 50%. And if we notice, the stable decay product, or the daughter product, accumulated. And at this one point, 50% is radioactive, 50% is stable. If you add those together, you have the sum of 100, which is the original amount. So we follow it down. This would be 5 times 10 to the 3rd years. Now remember, if you have your calculator, you could plug that in. You would put 5. You'd press that little EE button up here, E, and then you'd put in the superscript, not subscript, my apologies, superscript of 3, and that would give you the standard notation of 5,000 years. Now, most of these exponents, guys, because we're talking about old time or past, they're going to be positive. Positive exponents means large numbers. All right, here we are. We have potassium 40. It's going to decay to argon 40, calcium 40. And again, if this was a curve, I could actually draw what argon and calcium are going to be. We know that 50% is the first half-life. So this is what that curve would look like. And then it'd be 75% by the second, because again, the sum needs to equal 100. So it would just continue, and it looks like that. That would be the calcium or the argon there. Analysis of the rock sample shows that 25% of K40 remains. So you find 25% of calcium, or not calcium 40, potassium 40. K40 is potassium 40. And we follow it down, which would be 2.6 billion years. How much argon and calcium 40 would be left after 3 half-lives? So you can do a few things. We can start with 100, and that would be of our isotopes, which is K40. And then we could say that the products of AR40 and CA40 are here. This represents 0 half-lives. We'll do 1 half-life, 2, and then I can probably squeak a third down in here. After 1 half-life, 50% remains, and 50% becomes stable. We then take half of this 50 for the second half-life. There is now only 25%. The other 25 moved over and became stable, meaning 75% is the stable product or daughters. Again, 25 plus 75 equals your original amount of 100. One more half-life, 25.5 divided by 2 ends up being 12.5. So that's how much is left of K40. Remember, we started with 100. So whatever else is there is the AR40 or CA40, which would end up being, you could either subtract 12.5 from 100, or you could have added 12.5 to the 75 you had here. That means that 87.5% has decayed to the stable daughter products here. If you have questions, let me know. Let's take a peek really quickly at what we're doing. Google Meet 10:30 to 11. Remember, we changed that on Monday to accommodate those late sleepers. Please try and, again, set a schedule here, guys. Most of you are doing really well staying on track with your assignments. Some of you are getting stuff in late, and that's okay. This is new to everyone. I'd rather have it in late than not at all. So please just get it in, whether it's late or not. Finish up that review assignment, and do not forget there is a survey for it. It's technically assigned like a quiz on Google Classroom, but that is just so you get a better idea of where you stand. There's a couple more starters here that pretty much will work our way through, and I just wanted to leave you with one last thing before I let you go for the day. On the YouTube channel, I was just looking for some examples here. On the YouTube channel, go to the library, and you guys obviously can see some other things I've been looking at here for you. If we go to your playlists, there's an Earth Science one. Let's see if I can just access it here. Earth Science. Relative dating. Absolute dating. Some interesting videos here on review. So please feel free to watch them and get yourself a little bit of video review here. Tried to make sure they were not super boring for you guys. All right, other than that, let me know. Remember that if you get into your geologic time stuff, that was the page 8 and 9. All right, so if you're confused with that, let me know. Other than that, I'm going to let you go. This video is getting really long. All right, I will post these newer videos on the Google Classroom today, and let me know if you have questions. All right, guys. Happy Wednesday.